So welcome to the next session in my Modern Java by Example webinar series. Today, we're going to continue our discussion of the folders series of examples where we read the contents of a large recursively structured directory hierarchy. We build it into an internal representation that's stored in memory, and then we go ahead and perform various operations on that structure, such as being able to count the number of lines, search for words, count the number of entries, and other things you could do with a large recursive directory structure. Let me go ahead and share my screen, and we will get ourselves underway. So first of all, let me just do a quick recap on what the input to this program is. I've got this large directory hierarchy that contains all the source code for my various open source projects on GitHub. And as you can see, there's literally thousands of folders and files. And so what we're going to do here is read this all into memory using some clever techniques based on RxJava today, and then we're going to do the processing based on that. If you want to see the actual code that goes along with this, go over to my GitHub repository and go into the folders folder. And in there, you'll see there's a new subfolder called RxJava, and that contains the implementation we're going to cover. So now let's go ahead and switch over to the IDE. As you can see here, this particular example is going to re-implement the variants we've looked at for the past couple of days. The first variant of this program was based on sequential streams and parallel streams. The second example we looked at was based on completable futures with little help from the completable futures framework, sequential streams framework to kind of provide the structure for the asynchronous computations with completable futures. And now today, we'll be taking a look at how to use RxJava to solve this particular application. And as before, we're going to do both sequential and parallel structure here. And you'll see when you look at the code, I've designed it fairly cleverly to make it easy to switch back and forth between sequential and parallel processing in RxJava with very little change to the code. In fact, the code always stays the same, and I've got it parameterized. You'll also notice some other interesting things about this example, and we'll spend some time towards the end comparing and contrasting it versus the parallel streams version and the completable futures version. So without further ado, let's start taking a look at the code. So as before, there's a works subfolder or folder that stores all the recursive hierarchy on my file system, my local computer. Come in, do some parsing of the arguments, turning on verbose mode, for example. And then we're going to run the tests sequentially first, followed by running the tests in parallel. And you'll see that I have, as before, one way of doing this for both sequential and parallel processing. And when we're all done, we print the results out. So let's take a look at run tests. At a high level, the structure is very similar. We're going to start the test. First thing we're going to do is we're going to create a folder based on the root of our recursive directory hierarchy. And what we're going to get back from this is going to be a dirent to a folder. And we'll take a look and see what create folder does. Create folder actually creates the recursive folder in memory using the RxJava features. And so it actually runs asynchronously. So we get back from create folder a single to a dirent. And then we go ahead and do a blocking get here and end up with the actual folder itself. And I'll talk a bit more later about why I did it that way. I was trying to emulate sort of the asynchronous variants of this, but there's some little quirks or little features with RxJava that makes it a little bit more complicated than it does with completable futures in this respect. So once I've got myself a root folder that's snarfed all of the contents of the file system into the in-memory object, the folder object, we're ready to do the processing. So the first thing we do is count the entries, then we count the lines, and then we go ahead and search the folder for looking for a keyword. And you'll notice once again that we are going to be able to conditionally do this concurrently or sequentially. So you'll see how that gets done in a second. So let's go down here and take a look at create folder. And this is where the whole thing gets started. And so we'll go on a deep dive through the implementation in RxJava. At a high level, again, this looks very similar. We say folder from directory. We give it the path name to the directory as a file. And then we pass in the parallel flag. So let's go ahead and take a look at from directory and see how that's implemented. So you can see from directory returns a single. I could have had it return an observable, but there's no point. It's going to end up being a single directory entry, so I just used a single here. That means it's got one element in it as opposed to a stream of elements. What I do is I say observable from array, and from array is a factor method that's defined on observable, and it takes in an array and it converts it into a stream of observables. And what I do here is I basically say root path list files. So root path list files creates an array of the files at that level in the directory hierarchy. So not that big of a deal. A very straightforward thing to do. You'll remember when I did the implementation with the other variants, I'd used the files.walk method, which creates a stream. But I didn't want to use streams here because I'm doing RxJava instead. So I turned this into basically an observable from an array. Then I go ahead and I use the canonical flat map idiom in order to be able to let this run in parallel. If I was not interested in running this in parallel at all, I would have designed it a little bit more streamlined, but I'm wanting it to make it either run in parallel or run sequentially. So in that particular case, I did it the way we're showing here. So I use flat map, and for every file in the list of files, file could either be a directory or a file, I'm going to go ahead and use this idiom. So I use observable just to take that file and create an observable for it. And then I do a little clever trick here. I use the compose operation in conjunction with my RxUtils concurrent observable if. And so this is one of those things that will do something conditionally. So it'll make it a concurrent observable if the flag is true. So let's go take a look at concurrent observable if. So here's concurrent observable if. If we're trying to run in parallel, we go ahead and return the common pool observable, which as you can see does a subscribe on to use the common fork join pool. And if we're not running in parallel, we'd use the RxUtils or my RxUtils calling observable factor method. And what that does, as you can see here, is it's basically just a no-op. So it goes ahead and just returns the observable. So it's basically a no-op. So let's say that. So in that case, it's going to just run on the calling observable. It's not going to be concurrent at all. All right, so let's go ahead and step back here. So what this allows us to do is it allows us to conditionally convert this stream of observables into a concurrent stream, or not, depending on the flag. And that's very, very similar to the way that a Java Streams framework works with stream versus parallel stream, or the parallel method you can call to convert a sequential stream to a parallel stream. As to whether or not that's something that you want to always do, it's up to you, but I have a good time playing around with concurrency. And you'll see when we run the program shortly, it runs a lot faster when we turn the concurrent mode on. Then what we go ahead and do is we go ahead and filter out the root path to avoid infinite recursion. And then we do another flat map. And we do this flat map to make everything kind of work together properly. What we're going to do is we're going to call folder create entry, and we'll look at that in a second. And that's going to take the path that we passed in, and it's going to go ahead and return a durant, which will either, of course, be for a document or for a folder or subfolder. So that's what create entry does. So let's go ahead and take a look at create entry. And that is down here. So create entry checks to see whether the entry is a directory or is a file. If it's a directory, we go ahead and recursively call ourselves for doing folder from directory again. So that's going to go ahead and treat the entry as a directory, which it is because this check was true, and that'll recursively call itself on the next level down in the hierarchy, and the whole thing starts over again. If it's a document or it's just a plain old file, then we go ahead and say document from path. So let's go ahead and take a look at the from path method in document. You can see that this returns a single, so it's also intended to be asynchronous. And so what we do is we use our little trick here with the exception utils rethrow function adapter, and we're going to go ahead and read all the bytes from the file and return this in a new document object. and then we're going to emit that by using single just. So that goes ahead and creates that document, it emits it back, and that comes back as a single. So that's what create entry does. So create entry is basically going to end up creating the appropriate single for each of the elements that we have coming through this stream. And what we do then is we go ahead and convert this to an observable so we can flat map it back together. And then what we're going to end up here basically is a stream of observables, which will be durants. So we have a stream of observables that are durants. And all the code inside this outermost flat map can all be running concurrently in different threads in the common fork join pool. So that's how I've designed it, if the parallel flag is true, of course. When we're all done, we go ahead and terminate this stream, this flow, by using collect into. We go ahead and make a new folder with the root path as the entry point or the main rooted entry into this folder. And then what we're going to do is we're going to collect all the elements in this stream of observables by calling folder add entry. So create entry and add entry are two different methods. Create entry just creates a durant. Add entry will add the appropriate durant into the folder that was created here. So collect into is quite a bit like collect with Java's streams framework, except it's not quite as cool and extensible as collect is with collectors, but it's very much along the same lines. So let's go ahead and take a look at add entry. You can see what add entry does is it's going to take in the parent, which is the folder. And so we go ahead and just do a little cast here. And then we take the entry, which is the entry we're trying to put into the parent. And if it's a folder, we add it to the folder's subfolders list, and then increment the size based on the size of the entry because it's a folder, it's got recursive elements in it. Otherwise, if it's a file, then we go ahead and add it to the documents list and increment the size by 1. So that's basically what's going on here. And you can see that what collect into is going to return is going to be a single, because we've kind of basically merged everything together into one element. So we end up with this final single, which contains the hierarchy at that level. So that'll be the recursive hierarchy at that level of abstraction in the traversal of the underlying recursive directory structure. So eventually that'll pop back up and come back to the caller. So if we go back to main, you can see that that'll come back as a single to a durant. And then if you see where we use this thing up here, you can see that we call create folder, call blocking get, which will block, and then we'll go ahead and get back a durant. Now, I did a variant of this program where I returned the create folder as a single, and then I tried to use it much like you would use a completable future to be able to generate a bunch of other operations that take place off of that. And I was getting the strangest results. And the reason I was getting the strangest results is because the way that this works is you get what's called a cold observer. So everybody who comes along later and subscribes to it will get all the values that are emitted by it. And so it was cumulatively adding all the things every time one of the other methods would run. And it really was blowing my mind what was going on until I looked carefully at what was happening. And so then I realized I had to store this as a durant. So I'm still going to play around with that later, but I wanted to make it work properly for the demo. So what we're going to do now is we're going to go ahead and count the number of entries, count the number of lines, and search the folders using the durant that we got back from create folder. So let's go ahead and take a look at these pieces of code. And some of them are very simple, some of them are much more complicated. So here is count entries. So count entries takes a root folder. As before, what we're going to do now is we're going to use a different factor method on observer. And this is really interesting. This is sort of the equivalent behavior of a splitterator, if you will, with Java streams. So there's a factor method on observable called fromIterable, and it expects you pass it an iterable. So I made root folder be an iterable. So if you go over here and you look at folder, folder extends durant, and if you look at durant, durant extends iterable. And by extending iterable, it means it has to implement, or it can implement, the iterator method, because that is one of the things that gets inherited by iterable, from iterable. So what iterator does is it goes ahead and it makes a new breadth first search iterator for this durant, which of course will be the root one. And if we go down here and take a look at breadth first search iterator, you can see that that is an iterator that iterates over durants. And you can also see that it keeps track of the current entry, it keeps track of the folder list at a given level, and the document list at the given level of the current entry. And so when we make ourselves a BFS iterator, we give it the root folder, that becomes the current entry. We make a folders list and a docs list and throw the subfolders and documents into it. And then this is pretty much what we looked at the other day when we were talking about the implementation of the batch folder splitterator. This is basically a variant of the batch folder splitterator. It's kind of a stripped down version of batch folder splitterator. And you can see what it does here is it's got a hasNext method, which comes in and checks to see if the entry is null. Initially, it will not be null because initially it's going to point to the current entry, the root folder, in which case it'll return true because there are more elements. And then the next method is going to go ahead and store the current entry in the next dir, set current entry to null, and then go ahead and go to the next dir. So when we come back in next time, this time current entry is null, and then it's going to go ahead and start looking to see if there's elements in the folder list, other elements in the doc list, and it's going to go ahead and pull things out doing the reverse breadth first search model we've talked about in the past. This particular iterable is always sequential, and it doesn't have to do all the clever tricks that a splitterator does, where it breaks off chunks and sends them off to be processed in parallel for parallel streams, because we're never doing that kind of processing here. We're just always traversing through the elements sequentially. So that's a little bit different from the parallel streams model, where you can have parallel splitterators that'll split things up so things can run in parallel. That doesn't quite work the same with RxJava, for better or for worse. So that's what's being used here when we call observable from iterable. We're giving it a durant and we're implementing how to turn it into an iterable. So we're going to end up here with basically a stream of durants that'll come out of from iterable. And then we use our same trick to conditionally convert this to either be concurrent or sequential, depending on what the value of parallel is as the Boolean flag. In either case, we go ahead and count the elements, either concurrently or sequentially. And when we're all done, we use blocking get. And we use blocking get here just so it'll block until everything's finished. We get the count, and then we go ahead and print the number of entries in the folder. I also could have done blocking subscribe here and gotten the same basic result, but I wanted to use the blocking get just because I think it's a little bit more self-contained in this particular example. Okay, so that's count entries. So now let's go up and see other calls that are made here. Let's take a look at count lines. This one's a little bit more involved, but it's also kind of interesting. And it also, once again, reveals sort of the strengths and weaknesses of RxJava. So here's count lines. We take the root folder in and the parallel flag. As before, we go ahead and we convert the root folder into a stream of durants. So it's basically an observable that's a stream of durants. And then we use our flat map idiom to do conditional concurrency. So for each durant in this stream of durants, we're going to take each one, use the just factor method to emit it. Then we use the compose method with our concurrent observable if helper method to make this conditionally run concurrently or run sequentially. Now what we're going to do is we're going to filter out the documents. So we only want to deal with documents. So if you take a look here, is document is going to basically do this. It's going to check to see if the durant is a document. If it is, we're going to let it go through the filter. And then what we do is we do another flat map, and we're doing flat maps here to keep this to be an observable of whatever we want, as opposed to an observable to an observable to a single or whatnot. And we're going to use a little helper method here called split as observable. And we'll look at that in a second. And what we're doing here is we're going to split this, we're going to split the document up into lines. And we do that by giving it this regular expression. So let's go ahead and take a look at split as observable. Now, sadly, the string processing capabilities in out-of-the-box RxJava seem a little meager, to be honest, especially when you compare to the string capabilities that are available in Java Streams, which are less meager. For example, Java Streams has this cool capability called split as stream, where you can take a string and a regular expression, and it'll convert the string into a regular expression, into a stream, by using the regular expression to break the string up into pieces. There is no equivalent in standard RxJava, and the string libraries I found, like string observable, seem to be very outdated and don't work with later versions of RxJava. So that's kind of a shame. It seems like string handling is something that RxJava doesn't do as nicely as regular Java does. So, but no need to despair. We can write our own little program to do this, our own little method. So split as observable takes a document and a regular expression, and it gets the contents of the document, which is a char sequence, converts it to a string, and then we go ahead and call the split method on the string. And split is a method defined on a string that will convert the string into an array of strings by using the regular expression as a breaking pivot, if you will. It chops it up based on things that match. So what we get back there, of course, will be an array of strings that are split, in this case by new lines. And then we use the observable from array method to convert that into an observable for string. So now we basically have a stream of substrings that are emitted from this particular function. So armed with this, armed with the split as observable, we now end up essentially with a stream of strings, and then that correspond, of course, to the new line separated strings in the original input in the original document. Then we go ahead and count this. We count everything, and when we count, that ends up with a single to long. And then we go ahead and convert that back to an observable. So we end up basically coming out of flat map here with an observable of long, so basically a stream of longs that correspond to the number of new lines in each of the documents. We then go ahead and reduce everything using sum. So that'll end up with what's called a maybe. And the reason it's a maybe is because we might not have had any elements to begin with at all. So in that case, maybe it's got a result and maybe it doesn't. So in the case where it doesn't, then we're going to give it a default value of 0. So if there were in fact no elements, but there weren't in this case, but if there were no elements at all in our root folder, we don't crash, we just give back a 0. Otherwise, we're going to get the result of summing these things. And then you can see here, we go ahead and block until complete. So we basically block until we're done, and we store that result into the line count field defined here, and then we print out the total number of lines there. Okay, so that's basically count lines. Now, again, I'm sure there are other ways to do this, but what's particularly cool about this is the ability to convert it to parallel processing with the flip of a switch, basically turning on the Boolean flag. And we'll look at the performance implications of all this stuff in just a minute. The last method we're going to look at today is search folders. And search folders takes the root folder and the search word, and it does everything in parallel. So let's go look at that. It is going to follow almost exactly the same idiom as before. In fact, if I have more time, I'll probably refactor some of this code in order to parameterize it. So I'll have a common method that factors out all the things that are specific to the different operations I'm doing. And then I can just plop in these functions to do the different operations. As you can see here, we again take our root folder, we convert it into a stream of durants as an observable. We use the flat map idiom to run this concurrently or not. We emit each durant, compose it to make it run concurrently or not, depending on the parallel flag. We filter out anything that's not a document, so now we have basically a stream of documents. And then we apply flat map, except this time, rather than using flat map to count the new lines, we're going to have flat map call occurrences count. And this is kind of an interesting little helper method we'll see. It takes a document, it takes a search word, and it takes the parallel flag, and it will go ahead and call this method here called occurrence count. And what occurrence count is going to do is it's going to split the document up into words, and then it's going to filter only the words that match the search word. So we're going to end up basically with a stream of words that match the search word. Then we go ahead and count the number of times the search word appears in the stream. And then the last thing we do is we convert this back to an observable, and that's so that this will work properly coming out of this. So we flat map it, we end up with an observable to long, and then we do pretty much what we did before. We take all those counts for each of the document, search matches, we sum them all up, we get back a maybe, we give back a 0 if the maybe was empty, otherwise we give back the sum and we block until we're done, and that returns the matches, and we print those out. So that's basically what I wanted to show you. There was a few surprises, as I mentioned, as I was doing the program. And so it might be worthwhile to kind of talk about, sort of compare and contrast this approach with the alternative approaches we've looked at so far across a number of different dimensions. But before I do that, let me run the program so you can see what it actually does. And you can see that, in fact, it's able to do it all either sequentially or concurrently with the same code base, essentially. And you get very different results, which, of course, is what you expect and what you want. So if you take a look here, you can see that we start the test running sequentially. There are 2,200 files and folders. There's basically 121,000 lines or so. The word completable future appears 822 times. And by the way, these results are all identical to the ones you get if you run my other programs using completable futures or using Java concurrent or parallel streams. So that's reassuring to know we get the same results. And the same thing works both sequentially and in parallel. And then when we look at the performance, you can see that there really is a big boost from doing this concurrently. So if you take a look, the entries, let's take a look at one that's pretty important. So create folder. So you see when we did create folder in parallel, in other words, we did the traversal of the hierarchy, the directory hierarchy in parallel, it took 97 seconds to make the folder. When we did create folder sequentially, you can see it took about 800 milliseconds, I should say milliseconds, not microseconds, milliseconds. And so as a result, it's substantially faster. This particular computer is a quad-core hyper-threaded MacBook, and so it's able to get basically an n-fold speed up, which is pretty impressive, actually. Then if we take a look down here, you can see that search folders in parallel took about this amount of time, whereas search folders sequentially was about double the time. So we're getting a bit of a speed up, not an n-fold speed up in the number of cores, but a good speed up. And also, count lines sequentially and count lines in parallel. It's about 4 times faster to count the lines in parallel, which is an indication that it's also an embarrassingly parallel operation. So the point is that you can use RxJava. RxJava's performance is actually quite good, and it parallelizes very nicely. I would rank it, we'll say this in a second, I would rank it about roughly about the same complexity to program as streams. I think streams are a little easier to program because some of the stuff comes built in better with Java streams than with RxJava in some ways, especially switching between parallel and sequential is really easy with parallel streams. But once you put enough helper methods in place, like I've done here, you can kind of switch back and forth fairly easily. But the idioms are more complicated. The idiom for doing the processing in parallel is definitely more complicated for RxJava. Having to write this crazy idiom over and over again with flat map is kind of a pain. And even using parallel flowables is also somewhat awkward and limited compared to streams. So it's a little harder to write this code, I think, with RxJava than with streams. On the other hand, I would say it's probably easier to write the RxJava code than to write the completable future code. The completable future code is definitely more complicated. Now, this particular implementation doesn't use all the super cool features I used with completable futures. And it would probably take a while to add all those things into the RxJava code, because RxJava's not quite as sophisticated as completable futures with respect to completion stage methods and the semantics of things. They don't have a lot of the same things you find with completable futures in terms of all these cool methods like when complete and then compose async and then apply async and all this good stuff. You find yourself using flat map a lot. That tends to be the thing you use over and over again with RxJava. Pretty much any time I find myself in a situation where something isn't working, I change map to flat map and it starts to work. So you just, it's a different mindset. Flat map plays a bunch of different roles in RxJava, whereas with completable futures, it's a little bit more expressive. So that's the main thing I wanted to walk through here. I'll take some questions, and then I'll probably, if there's time, kind of compare and contrast the implementations of the different variants of the solution, and we'll see how they appear. So let's go ahead and see what questions we have. So let's see. The reduce API returns something similar in Java streams. So something similar to optional. So I'm not sure what you mean by reduce. Oh, yes, I know what you mean. Okay, so let's go ahead and take a look. That's a very good question. So got to go back here and share my screen so that we all know what we're talking about here. There we go. Okay, so now let's pop back over here, and you'll see that what I'm talking about, what's asked is reduce. So a maybe is basically like an optional in Java streams or in Java 8, modern Java, if you will. And so reduce returns a maybe, which is kind of like an optional. And then default if empty is kind of like the or else method on an optional. So yes, that's correct. That's very similar for a lot of the same reasons. Let's see. Let's take a look at some other questions. Can multiple threads read concurrently one file? So this particular program is not trying to read the file concurrently. What it's basically doing is it's using different parts of the file system and then reading those things concurrently. And the answer, of course, is yes, you can do that. It's also possible to read files concurrently as well, although that's not something that we have to do for this particular program in order to get it to work properly. It still works quite nicely with the existing approach without having to do concurrent reads on the same file. We're using different paths in order to read different files concurrently, which works perfectly fine. Let's see. So there's a follow-on question to that asking about if you were to read the same file multiple times, then you'd have to use locks, and that's correct, but that's not what we're doing, because if you think about what we're doing here, we are basically reading different files. We're just reading in different parts of the file system at different times using the mechanisms that are provided, in this case with the list file or list files method on a path. Let's see. The timing calculation for completable future was done using join. That's correct. That might not give the correct value. Whoops. Didn't mean to do that. Hold on. That doesn't give the correct value of the underlying completable futures before the join call. That's correct. So that question actually stems from the example we gave yesterday, where we were showing the completable futures version of this type of program, the folders program. And with the completable futures version of this type of program, as we were seeing, the asynchronous operations all ran very fast, and then the bulk of the time was spent in join. So that's correct, but that doesn't really correspond to what we're dealing with today with RxJava. But it's a correct statement. In the previous examples, you specified thread pool almost at every level. This program does not seem to do too many similar calls. I'm not really sure what you mean. So in the previous, all the programs I've done so far by and large, especially the last several, have all used the common fork join pool. And so the version that used parallel streams, which we did 2 days ago, that of course used the common fork join pool because it used parallel streams. And with parallel streams, you have no choice but to use the common fork join pool. Well, or limited choice. That's the typical thing you have to do. For completable futures, which is the example we looked at yesterday, we used supply async with its default parameter. And we also used, I think it was then compose async with its default. And that will also use the common fork join pool. So common fork join pool was used there as well. As you saw today, we again used a scheduler in the RxJava framework that's connected with the common fork join pool. So all 3 examples used fork join pools. They all work exactly the same way. So all right, so there's, I'm still not really sure I understand your question. Let me go back to the code though, and show what I'm talking about. So the code that we're seeing here for the RxJava version is using this super clever concurrent observable if helper method in conjunction with the compose transform method that's built into later versions of RxJava. And as we showed, it's basically returning either the same observable with nothing done to it if we're not running in parallel, or it's returning an observable that's been scheduled to run on the common fork join pool. And much like the way that parallel streams works, where you have to explicitly say, I want a parallel stream, please, we're doing the same kind of thing here. So this code is actually very, very similar to the code that we showed with the version of streams where we would toggle back and forth between sequential and parallel streams. And we're actually going to look at that code in just a second. So that might help to clarify what you're asking. So that's actually probably a good segue to go over here. If I can bring up my editor somehow. Let's go ahead and shut this down and shut this down. And then let's see if we can make, there we go, Emacs pop up. I like to use Emacs for this type of thing, as you'll see, because it's much easier to switch back and forth and show different parts of my screen. So let's take a look. So here is the RxJava version. So let's go ahead and go down and look at the RxJava code. And we'll look at the main code because that's probably a good place as any to look. And then let's go do the same thing for sync, which, as you'll see, is the one that does the streams and parallel streams version. So these are the 2 different versions that we've got. All right. So you can see, at a high level, the code looks very similar. We start the tests, we warm things up, and so on and so forth. And then you can see the tests that run. They also look very, very similar, almost identical, in fact, in both cases, just little syntactic differences here and there. If you take a look at create folder, you can see that create folder works very similar in both cases. It looks almost identical. Things get interesting when we start getting into the actual different methods that do something. So here's count entries for the RxJava version on top and count entries for the parallel streams version down below. So you can see the differences here, right? So up here we use Observable.fromIterable, which goes and uses the iterator we defined on our Durant class to get every element. Whereas down here we use the root folder.stream method, which under the hood calls a splitterator. And you can see here how we can conditionally convert this to be a parallel splitterator or a sequential splitterator just by turning on the parallel flag. And that's actually sort of like what we're doing here, where we're using the compose method. So it's not quite the same, but it's similar. The reason why it's not quite the same is that using a parallel stream, of course, will make the splitterator itself create things that will run in parallel. So right from the start, we're splitting things up at a finer grain level of concurrency right from the very beginning. And then down here, we go ahead and do the count, and then we display the results. So, but I think you'll agree that these two pieces of code look very, very similar. One's a bit more asynchronous than the other. The RxJava one's a little more asynchronous. The parallel stream version is more synchronous, but both of them can toggle back and forth between sequential and parallel programming or concurrent programming with very little change to the code once you know what you're doing. But you'll notice that with parallel streams, it's built into the parallel stream abstraction to toggle, whereas with RxJava, I had to do a little trickery on my part by making this concurrent observable if factor method that selects between the appropriate level of concurrency. Things get much more interesting when we move to more ambitious methods. Like, let's go take a look at search folders, for example. So here's search folders with RxJava, and here's search folders with parallel streams. So you can see that in both cases, we start out by getting the elements we want to search, getting the directory elements we want to search. One uses from observable, one uses the stream factor method, which hits the splitterator. Again, it's really easy to switch over to be parallel here. With the RxJava version, however, you can see that we have to write this somewhat wacky idiom if we want to get things to run in parallel. And once you know the idiom, it's not that hard to do, but you've got to write the code. Whereas with parallel streams, you just say .parallel, and boom, you're off to the races. So this is kind of where the idiom goes. You can see we use the compose method like we use parallel here to turn on parallel processing. We filter the results. We do flat map here with occurrences count. We do map to long here with occurrences count, right? So this is looking very similar. The main difference is that this occurrences count here, if we take a look at it, actually itself can run in parallel too. So we can do all the parallel processing there if we want to. Whereas the occurrences count here was sequential, and that's because when I tried to do the same trick with the idiom, it just was very slow. So I thought that wasn't worth it. Let's see. So if you take a look down here, pop back up, you can see the occurrences count here. When we're all done, we take the stream of longs that came back from map to long, and we sum them together. Whereas with the end, we get a result, right? That comes back as a long because it's not asynchronous out of the box the way that RxJava wants to be. With RxJava, we ended up with this observable of longs, which we reduced, which is kind of like sum. And then we had to play a little trick to see if it was empty or not and return a default. So it's a bit more like an optional in that case. So I think that the clear winner in terms of parsimony is Java parallel streams. But if you want to be able to mix concurrent code and asynchronous code, the RxJava stuff is more asynchronous out of the box in some ways. So that's basically how I would compare and contrast these two pieces of code with respect to parallel streams versus the RxJava implementation. And you can see the RxJava stuff is just more verbose, but they both perform very well. And so the key take-home point here is if you know what you're doing, you can write very efficient code with either of the approaches. Okay, so that's really what I wanted to show. We could also kind of step through and compare and contrast the asynchronous versions of things. But it's, I should say one more thing. So the other thing that's worth noting about the version that's the parallel streams version, let's go ahead and split this back again so you can see the different implementations. Let's go look at the folder implementations for both of these things. And now, of course, I've got them backwards. So this is the RxJava version. And let's go ahead and bring over the parallel streams version if we can. Okay, is that the right one? I've still got the wrong one. There we go. That looks like it's right. So let's go into folder and grab folder. So it's kind of fun to take a look at the differences between the from directory implementations between RxJava and parallel streams. So again, RxJava is on the top, parallel streams is down below, or streams and parallel streams is down below. So first of all, notice how we use the root path list files factory method to get the list of files at that path. And remember, this is not sharing a common file. This is all the different files in the recursive file system. So there's never any contention. We're not opening the same file twice. We're opening different files. So we don't have any contention. We don't have to lock the files individually. Down here, we use the streams walk method that's defined on files. So we get a stream right away. Whereas here, we have to go ahead and convert the list of files into an observable using the from array factory method. And then once again, look at how easy it is to turn this into a parallel stream with parallel streams. So we just say parallel stream or path stream.parallel. Whereas with the RxJava version, we've got to do this idiom again. Same basic idea. Here's where things also get more complicated as well. The way that we do all the processing in the streams-based version is by using a collector. And collectors combine several different capabilities. They automatically will create the appropriate accumulator, which is the mutable result container, and then they will accumulate into it. And then when they're done, you can finish things up. So there's certain things that kind of come built into collectors that make them really concise. With RxJava, they don't really have the concept of a collector in quite the same way. So we had to do a few other kind of fancy footwork here by making a new factory method called create entry, and then have that stream through. And then we do collect into. So the way to look at this is that the streams approach has a bit more structure to it. So there's the concept of a collector. There's a concept of a splitterator. You can control the creation of streams from a source with splitterators, and that can run in parallel. You can control the merging together of substreams with collectors, and that's configurable. RxJava doesn't quite give you that level of control. You can do it, but it requires a bit more work on your part in a more idiosyncratic way. It doesn't come out of the box defined as crisply as you get with splitterators and as you get with collectors. But you can do the same capabilities. And I think that's really the key point I want to make here is you can get the same capabilities with both frameworks. It's just that one is a little bit more baked in. The Java Streams one is a little more baked in, whereas with RxJava, you have to do a bit more kind of idioms on your part or patterns to apply things to work in the way you want. Okay, so those are the things that I wanted to cover. Let's see if we have any other questions. Let's see. In the earlier examples, there were lots of calls to compose apply schedulers. This implementation seems not to have as many calls. Well, yes and no. That's worthwhile going back and looking at real quick. It turns out that the earlier implementations that I did had just the same number of calls. It's that my implementations was not as clever as it is now. So this is the clever version that we have now. And let's go look over here. Let's go look at the version that did the web crawling. So if we go up here to RxJava, and let's see, I think it was EX4. Yes, EX4. So here's the EX4 version of this stuff. This is the image counter example we looked at maybe a week ago or so. And this is RxJava, and let's take a look at Compose. So if you take a look here, you'll see that I use pretty much the same tricks in the same ways. So anytime I want to have things run concurrently, I basically give it a scheduler to do so. And so I think if it looks like there's more stuff, it's just that there were more things that were going on kind of at the same time. But it's really the same basic idea. Whenever you need to run things concurrently, you need to turn it on. It's just that particular program was a little bit different in the way it was designed, but same basic concepts and how things work. Let's see, if you go back, yet another example, I think this was EX2. This is one that we definitely looked at. I think it was the first week we'd done this stuff. So this is the one that shows off the different ways of doing parallel processing or concurrent processing with RxJava. So the two ways of doing it are with, let's go down here and take a look at this. One of them is by using this flat map idiom, which is what we see here. And the other one is by using parallel flowables, which is what we see here. I've been focusing more on the flat map idiom because it's easier to toggle things to be sequential versus parallel or concurrent with the flat map idiom than it is with the parallel flowable. With parallel flowables, once you commit to parallel flowables, it's going to be in parallel. Or it most likely will be in parallel. I guess you could play some tricks and have the thing run in the trampoline scheduler, which would always be the same thread. But it seems to be more like you're really dedicating yourself to be in parallel when you use a parallel flowable. Whereas with the flat map idiom, you can toggle back and forth. You'll see the main difference between this example and previous ones, however, was back in those days, a week or two ago, I didn't have as cool of a framework for this. So I would just sort of hard code, subscribe on schedulers from fork join common pool down here, just kind of hard coded in there. So that's going to run concurrently now. Whereas nowadays, with a little bit of thinking about it and reflecting on other techniques I've seen applied here, I can parameterize it in a much more convenient way. So that's really the main difference. But I think the point that's worth making is that with RxJava, running concurrently requires a bit more thought than with Java streams. With Java streams, running concurrently is drop dead simple and often requires minuscule changes to the code to go from sequential to parallel, whereas with RxJava, it takes more foresight. And of course, once you know the idiom, it's not that hard to do it, but you do have to kind of stop and think and type it in. Now, also keep in mind that just for my own personal style, I like to be able to toggle. So that's important to me because I like to be able to see what speed up are we getting from using concurrent processing on my multi-core machines. If you're not interested in doing that, if you're interested in doing other things and toggling between concurrency and parallelism or between sequential programming and concurrency is not important to you, then the kinds of things I'm doing here would be probably overkill, quite frankly. Let's see. So we're getting towards the end of today. I was very pleased with myself having implemented the RxJava stuff in about a day. It was a little vexing at first, but I managed to get it done. I'll see if I can do one of the reactor framework things maybe next week. I've got some other things I've got to do, so I can't spend all my time doing that. If someone wants to take a shot at converting the RxJava code to reactor code, that would be fantastic. Then I'd be happy to talk about it. It's also my experience that the documentation is somewhat lacking for the reactor framework. Actually, to be honest with you, the documentation for RxJava is somewhat lacking as well. Much easier to get good documentation and up-to-date stuff and complete documentation for all the Java streams code and completable futures code. Much easier to understand those things. It's been a bit of a scavenger hunt getting some information about some of the features. You have to do a lot of reading and poking around, and RxJava seems to be a bit more in flux. But that's okay. That's cool. It means that they're innovating and evolving and so on. So we'll see how it goes, whether we have time to do that or not this week. What I'm looking forward to doing tomorrow, let's see. Go ahead and share my screen one more time. So what I think we're going to do tomorrow is I think we're kind of done with this example for the time being, but we have a bunch of other fun examples that we can look at, assuming that GitHub stays up. GitHub has been really flaky lately for various reasons. So I think what we'll probably do is either look at the EX8 example, which shows off a whole boatload of cool completable future features that we haven't looked at in as clear detail yet. We've kind of glossed over some of this stuff. Or depending on how things go, we might take a look at the EX22 example, which shows off a whole pile of cool fork join pool programming idioms. Both of them are interesting to learn about. Both of them are interesting to talk about. So we'll kind of flip a coin and see how things go. And with that, I think I'll wrap it up. We're kind of getting to the bottom of the hour. As always, I really appreciate everybody showing up and asking questions. And look forward to talking to you guys again soon. And don't forget, all this stuff will be up on YouTube here very shortly. So thanks again. Take care.